Let's try problem 3. We want to sketch the curve defined by these parametric equations, and in this case we have a finite interval for the variable, so we will have a finite portion of a curve, and we'll indicate here the direction in which the curve is traced out. We'll set up a table similar to what we did for example 1, and that will give us a picture for what these parametric equations give. So we start by setting up the txy table. And here we're told that t ranges from -2 to 3. So just to get a picture of what's going on, we'll just choose integer values here. -2, -1, 0, 1, 2, 3. Now, once again, our x function, x of t, is 4 minus t squared. The y function is 2t plus 1. So we'll fill in this table to get pairs of points, which we will then plot in the xy plane and join with a smooth curve. So starting with the x values, we have 4 minus t squared. So our first x value is 4 minus -2 squared. -2 squared is 4. 4 minus 4 is 0. Then 4 minus -1 squared. 4 minus -1 squared is positive 1, so we have 4 minus 1, which is 3. 4 minus 0 squared is 4. 4 minus 1 squared, 3 again. 4 minus 2 squared, that's 4 minus 4, so we have 0. And then 4 minus 3 squared, that's 4 minus 9. So -5 is the value here. Once again, the way to get the x values is by plugging in the corresponding t values into this equation for x in terms of t. So here are the x values of the points, and now we'll find the corresponding y values. So first of all, y equals 2t plus 1, so we plug in -2 for t. So we have 2 times -2 plus 1. 2 times -2 is -4 plus 1 is -3. Then 2 times -1, that's -2, plus 1, we have -1. 2 times 0 is 0, plus 1. 2 times 1 plus 1 is 3. 2 times 2, 4, plus 1, we have 5. And finally, 2 times 3 plus 1, 2 times 3 is 6, plus 1 is 7. So here are the corresponding y values. Once again, these give us xy pairs. We have 0, -3. We have 3, -1 here from the second row, 4, 1, 3, 3, 0, 5, and finally -5, 7. These are points that lie on the parametric curve defined by these equations. Now let's use these points to plot what the parametric curve looks like. So x ranges from -5 to 3. And y ranges from -3 to 7. So we'll just get a rough sketch of the curve. The first point is 0, -3. So 0 in the x direction, -3 in the y direction. We have this point. Then 3, -1, that's right here. Then we have 4, +1. Oh, we need one more tick mark for the x. 4, +1, that's right here. And then we have 3, 3. 3, 3 is right here. And then 0, 5, 0, 5, right about there. And then -5, 7. So -5 in the x direction, 7 in the y direction. That's right about there. So here are the points that we found by plugging in various values for t into the x and y equations. And we can imagine connecting these with a smooth curve, and it looks like it will probably be a parabola, which indeed is what the shape is. So the parametric equation looks like this. Now, this is only a finite portion of the curve. T, we were told, ranges from -2 to +3. And when t ranges from -2 to +3, this is exactly the curve that is sketched out. So we only have a finite portion of the curve. We were also told to indicate the direction that the curve is traced out. So as t gets bigger, the points move from down here, moving around the curve this direction. So we can indicate a direction to this curve by adding an arrow here. So the curve is traced out in that direction. And we can imagine that this could be describing the trajectory of some object. The arrow here tells us which direction it's going. Parametric equations are very useful for describing trajectories. Now, for example 4, we want to eliminate the parameter to find a Cartesian equation for this curve. So to eliminate the parameter, we solve one of these equations for t and then substitute into the other. Now, it doesn't really matter which equation we solve for t, but in this case it will be a little bit easier to solve the y equation for t. So here we are solving example 4. We're going to solve the y equation, y equals 2t plus 1 for t. So y minus 1 equals 2t, and then divide both sides by 2, we have that t is y minus 1 divided by 2. We can take this expression for t, substitute into the x equation, and we will have a Cartesian equation of this parametric curve. So x of t equals 4 minus t squared, and now we replace the t with y minus 1 over 2. So we have x equals 4 minus y minus 1 over 2 quantity squared. This is a Cartesian equation for the parametric curve. If we were to plot this, we would get an entire parabola here. There would not be a finite portion and there would be no direction, but this is the corresponding Cartesian equation for this parametric curve. Let's take a look at this in Desmos. So to start off with, let's talk about how to plot parametric curves in Desmos. It's pretty easy to do, actually. You start by thinking of an ordered pair, and normally if we just enter values here, then we just get a point. But instead of just entering constants, we are going to enter the parametric equations. So the x equation is 4 minus t squared. Desmos recognizes t as a special value. So we'll enter the x equation, now the y equation, 2t plus 1. And right away, Desmos gives us a portion of the curve, and the parameter ranges from -2 to +3. So there we have it. There's the parametric curve that we just plotted by hand. And we can plot the Cartesian equation, x equals 4 minus y minus 1 over 2, quantity squared. So there's the Cartesian equation, that's the whole parabola, but that's losing out on the finiteness of the curve, and we're also losing the direction with that parabola. So let's talk about the directionality of this curve here. How can we visualize that? Well, I'm going to plot the same thing, but I'm going to change the label here to be capital T. And capital T is not recognized by Desmos like small t. So if I add a slider here, then this gives me a point, which I can see moving along the curve. And this point, this is how the curve is traced out. As the parameter values range from -2 to +3, that point is tracing out the curve. And we could even visualize the whole curve being traced out. We start at this point down here, and as the parameter increases from -2 to 3, the entire curve is traced out. So the direction of this curve loops around this way. We can easily see the direction, we can see the finiteness of the curve. Desmos is actually a really great tool for plotting parametric equations. So I encourage you to be comfortable with how to plot parametric equations in Desmos. It's pretty straightforward, and it's a really fantastic way to visualize what's going on here. Now, before we get to further examples, I wanted to show you just how cool parametric equations are with some really neat examples. So to start with, let's take a look at this parametric equation. We get a spiral. And if we change this up a little bit, if I do the same parametric equation but just make the x component negative, then we get another spiral. And this just looks trippy and cool. Don't bother, by the way, about trying to understand all these expressions here. These are very complex parametric equations. And if you want to pause the video so you can read the equations and copy them down and try them on your own, then go ahead and do that. But don't bother about where these come from. Some of these have special names, and they're all very cool. So here we get these spirals, and we can see more of the spiral is traced out as the parameter increases. Okay, what else do we have here? We have this shape. There's some special name for this. I don't remember what it is, but we could vary some of the variables here and get slightly different looking similar shapes. So that's kind of cool. And then this, it's like petals of a flower. And then this, like a starburst cool shape. Notice that most of these are using sine and cosine because the periodic nature of those functions makes some really cool looking overlapping graphs. Check out this one. Isn't that cool? We could vary the different values here and we could get different looking spirals and curves and circles. All right, how about this? Oh, that's so exciting. It's a circle. Well, watch what happens when we change this value of this constant n. We get all this stuff. So that's pretty cool. This next one is just trippy. Starts off kind of looking like a triangle. And let's just look at the definition here. It's pretty simple. Here's how this is defined. So we have trig functions inside trig functions, and we're adding this constant a. We could actually think of this as another parameter here. And as we change that constant a, watch what the graph does. It just goes crazy. So we get this super cool looking loop-de-loop, just a wild looking parametric graph. Now notice that basically all of these are not functions of y. They're not y as functions of x. These terribly fail the vertical line test. So it'd really be impossible to write a Cartesian equation for this sort of a graph. It's really only something that we can do with parametric equations, and it's just really cool looking. All right, and last but not least, if we take these parametric curves here, it's kind of complicated. What's this going to be? Aw, it's a heart. That's super cute. Just how cool, trippy, and cool. They're all very cool. So that's kind of cool. Like a starburst cool shape. And really cool looking. Isn't that cool? So that's pretty cool. Super cool, and it's just really cool looking.